Okay, thanks very much for that presentation. That was great. Our next speaker is Robert Kohn. Robert is a Scientia Professor in the School of Economics at University of New South Wales. Robert is a Chief Investigator in our Centre of Excellence for Mathematical and Statistical Frontiers. He is also a Fellow of the Academy of the Social Sciences in Australia, and his research and teaching interests include Bayesian methodology, variable selection and model averaging, non-parametric regression techniques, time series modelling, multivariate Gaussian and non-Gaussian regression, and Markov chain Monte Carlo simulation algorithms. Robert's one of those people that you can ask pretty much any question and he will give pretty much any answer. So I'll call him to give his presentation.
Thanks very much, Kerry. The answer will have no relation to the question, but so I've got all this water in front of me. Okay, so I'm going to talk about, what I'm going to talk about, big data, big models, intractable likelihood. And I'm part of the centre. Now, I just want to acknowledge this is, what I talk about is joint work with Mike Pitt, University of Warwick, Min Gok, who's a postdoc at UNSW, and Min Gok is in the audience somewhere. And Matthias Quiros, who's a PhD student at Stockholm University. Matthias Villani, who's a long-standing co-author of mine. He's at Linköping University, and David Knott from NUS, and Anu from Oxford. So I'm going to organise the talk in this way. First of all, I'm just going to talk briefly about Bayesian inference, because you probably know about this. I'm going to talk about intractable likelihood, and in fact, that can be estimated unbiasedly, and actually the whole talk revolves around this idea. I'm going to illustrate the intractable likelihood idea with important sampling example. I'm going to talk about intractable likelihood with a time series example, and I want to, as an illustration of a hard problem, I'm going to talk about subsampling for big data, big models, and I'm going to talk about variational Bayes a little bit. And the way I want to tie it in together is, first of all, I want to talk about just the idea of intractable likelihoods and estimating them unbiasedly. And second of all, I want to sort of say that the same sort of questions can be applied to not only big data, but complex models. And often we have both a complex model. So when we have a complex model, we might want to use these techniques and also combine that with big data. For example, Rob talked about time series, like hundreds of millions of time series, but the question there is, okay, we've got so many time series, many of them are from the same location. Do they share the same parameters? Can we do some random effect stuff? Can we actually do some variable selection? So all of a sudden, instead of just having lots and lots of time series, we've got lots of time series with a more complex model. And that becomes an interesting problem in itself, because we want to, when we tackle big data, it's not just a question of summarizing it. I reckon it's also maybe it's also a question about thinking about how to structure the model in order to handle it in a more efficient way, maybe through clustering, through random effects, the Richelet process stuff, maybe through spike and slab priors that reduce the number of parameters in the models as distinct from shrinkage priors that still leave most of the parameters in there, it's just that we do some nice things with them. And another aspect of that I'll talk about, I'll talk about a time series example, but again, what I hope is that the sort of methods that we're sort of dealing with very simply, and this is a hope, that we're dealing with very simply in time series now, but they're complicated models, will actually generalize to spatial temporal models where the models become more complex, and what we really want to do is apply these new sequential Monte Carlo particle methods to be able to tackle models that, so another theme that I won't talk about that much here, but inherent in all of this is that we properly want to develop tools, and I think we are developing tools, where we estimate the models we really want to estimate rather than the models that we contractably estimate. So particle methods and SMC, and Steve talked a little bit about that. We want to estimate the models people are really interested. So we want to start with a model, economic model or physical model that we're really interested in, rather than the stuff that's sort of tractable, linear regression type stuff, AR stuff. The final part of the talk, if I get to it, but actually there's nobody after me, so that just delays the lunch. And so I'm not going to try for a joke, I'm just going to do it ad lib. But the final part of the talk is a bit about variational Bayes. And what we want to do is we want to have a Bayesian structure that we want to retain as long as possible, and then maybe take some shortcuts about, if we do distributed computing, we can put the stuff on various machines and then use maybe at a later stage of the analysis, use some approximation ideas like variational Bayes with intractable likelihood to actually do the estimation. And okay, so just a review. So with Bayesian stuff, we've got observations Y, they're independent or correlated. The density of Y given the parameters is called the likelihood, and we write it as P of Y given theta. The prior on theta is P of theta, and the posterior is defined as pi of theta in this way. And Markov chain Monte Carlo, and especially Gibbs sampling and Metropolis Hastings, is a way to estimate these models that's freed up a lot of, we can estimate interesting models, big models now, because of we run a simulation, and that simulation converges eventually to iterates from the target, which is pi. And the way that, so suppose we're currently at theta current, and we generate some proposal, Q of theta given theta current, then we accept, then we generate theta p from Q, and then we accept theta p with this probability, and that ensures that we eventually converge to the target, and this is the sort of magic formula that that sort of ensures that everything works. So even though we're using approximations, we're getting to the exact solution. And MCMC has had a profound effect on Bayesian analysis and more generally on statistics. But sometimes it's difficult to compute the likelihood. Sometimes it's very expensive. So everything still works if we replace the likelihood by an unbiased estimator. And so one way that I'll talk about is when the full likelihood is very costly to evaluate. By unbiasedness, I mean that p hat y given theta u are the random variables that allow us to estimate. And then when I integrate u out, I'm going to get p of y given theta. So u can be generated from a density that depends on both y and theta. That's still okay. So the u's are the auxiliary variables. And the trick is, and I'll do it briefly, the trick is that we just augment the space so that instead of just having theta, we've got theta and u. N is a parameter, number of particles or number of important samplers. The trick is we augment the space in such a way that we're now dealing with a bigger space, theta and u, whose marginal density pi n tilde theta is exactly equal to the density we are interested in. And so the idea with pseudo marginal Metropolis Hastings is that we replace the likelihood by its estimate, and that's how it sort of works. So basically we generate from a proposal, and instead of evaluating the likelihood exactly, we evaluate the likelihood, an estimate of the likelihood. And then we do Metropolis Hastings in the same way as we do before, and accept or not accept the iterate, and then we just go on. So all we're doing is, and this is a key that's very important, we are simulating from an augmented space. We are simulating from an augmented space whose marginal for theta is exactly what we want. And so for latent variable models, it's really easy to see. Suppose we've got importance sampling. We want P of y given theta. We use importance sampling here, where Q of theta x is the importance sampler. And in this particular case, what we get is an unbiased estimate of the likelihood in this way. And the particles are really the xk's generated from Q of theta. So in many situations, like the particle filter, is just a variation of sequential importance sampling. So the idea is that we replace an estimate of the likelihood by an unbiased estimate. The talk or the treatment can be generalized because not only, actually I can look at this now, not only can we use Metropolis Hastings for this, but we can also use Gibbs sampling in an augmented space in the same way. So that what's that? I'll move. I can stand here actually. Move the mic around. This is great. And so importance sampling. So the use of the XKs generated in this way. And I want to talk a little bit about this because I'm talking about a complicated, small data, complex model example. But the hope is, and Noel Cressy and Lawrence Murray have done some of this on spatial temporal data, my hope is that by soon and even now, we can tackle really large problems in various guises of this particle methodology. So in the particle filter world, what we do is when we run the particle filter, we get, and the particle filter provides us. So in any sort of latent Markov process, hidden Markov model or more complicated, the particle filter provides us with an unbiased estimator of the likelihood, and we can use that unbiased estimate of the likelihood to actually then do the Bayesian inference. Now, and we've also used it, but I won't discuss it today, models, say large factor models, large dynamic factor models, gauge factor models, where it's quite difficult actually using regular MCMC methods. We're using particle filtering, particle Gibbs to actually do the estimation. And I just want to set up I want to just discuss very briefly this model. I'll just show you this model. This model is an example of a complex model that's hard to actually estimate using MCMC, but with Euler discretization, it's very simple to use particle methods with unbiased likelihoods to actually estimate the model. Now again, this is a complex small model. What I'm hoping, and I think we've got some evidence of this from some of the stuff we've done, but I won't go through that now. What I'm hoping is that the sort of particle methods we're developing and the corresponding approximation through variational Bayes will let us handle these sort of models, but on a much larger scale. And so here you've got the returns are modeled in continuous time. The observations are discretely observed. We've got two driving forces, V1 and V2, which are driven by Brownian motions and are actually correlated. It's a complex model to estimate. Without MCMC, you can't do it. With MCMC, you can do it, but it's very, very difficult. With particle methods, it's sort of not difficult at all. And the Bayesian inference is on these parameters. And what drives a lot of the analysis, but not all of it, but what drives a lot of the analysis are sort of two assumptions that we make. One of them is that the density, so let's say that Z is the error in the log likelihood. Z is the error in the log likelihood. That summarizes everything, all the use of Z. So Z is the error in the log likelihood. And what we're assuming, and the reason for that is not bad, it actually stacks up pretty well in lots of examples, is that the error is independent of theta, and that the error is normally distributed. And the reason that it stacks up is that basically you've got a central limit theorem going for you when you're estimating the log likelihood. And I'll talk a little bit more about that later on. And the practical guidelines are very simple to what we do. At least that's the practical guidelines 2014, not the practical guidelines that might be there in end of 2015. The practical guidelines are that you select sigma equals 1.0. Sigma is the variance of the log likelihood estimator. And when you've got no clue about the proposal, you select sigma equals 1.0. When the proposal is good, you select sigma equals 1.0, and when the proposal is poor, you select sigma equals 1.7. So basically, we're estimating the likelihood unbiasedly. Z is the error in the log likelihood estimator. If our estimate if our proposal distribution is poor, there's no point having a very accurate estimate of the likelihood. So by optimality, I mean for a given accuracy, how large should we choose the number of particles in important sampling, or N more generally, such that in order to get the standard deviation to be of some form. So when the proposal is poor, we would choose sigma equals 1.7. When the proposal is good, we choose 1.0. And generally, we advocate choosing, theoretically, we advocate choosing sigma equals 1.2 or even less, because we're still making assumptions. But you don't have to have n equals infinity for the number of particles. That's pretty pointless. After you've chosen n in such a way that sigma is about 1, there's no point being more accurate. Okay, so I'm going to talk about this. This is the second part of my talk, and I've got about 20 minutes left, right? 10? I thought I had 40. 20, right? Yeah, that's so 20, right? I'm not sure. Yeah, so, okay. So, because I've got, it's not so much that I've got so much to say, but I've got 5 glasses of water in front of me. So this is the second part of my talk that relates to the first part. And so now efficient data subsampling. So I've got parameters, I've got data density with P of y, K for the kth, and I've got the likelihood, and that's my posterior. One reason why MCMC is so expensive is that we need to evaluate the posterior, the likelihood at n terms, and if n is large, that's massive. So what we did with Matthias, and Matthias is borrowed from survey sampling, and so I suppose we've got all firms, n firms in Sweden. They wanted to know how to estimate certain aspects of the population. And in our case, what we are doing is that we've got the log likelihood. We want to evaluate the log likelihood here, but instead of evaluating each time, why don't we estimate the log likelihood? Why don't we get an unbiased estimate of the log likelihood instead of getting the full log likelihood? Why don't we subsample and get an unbiased estimate of the log likelihood? Now, the two most important aspects of this is how do we select the subsample and the sampling scheme, and also, I guess, it says down here estimator, but so we want, in some sense, to get an unbiased estimator of this. And the other thing we want to do is we want to be able to estimate its variance very quickly, because I want to use my theory from the previous part to get the variance down of the estimator down to 1, or a bit less than 1. So survey sampling plus MCMC, take a random sample of size m and compute an estimate of theta. And therefore, I have a procedure, a method. So, what I want to discuss is data subsampling, constructing an unbiased estimate of the log likelihood. the particles in my case become the subsampling indicators. So now I'm just doing a straight likelihood, and now already in 2013 and even before, people suggest that doing simple random sampling on the log likelihood. They dismiss that, and the reason is that it just doesn't work. So simple random sampling doesn't work. So you've got to be a lot smarter than that. The variance becomes huge. So simple random sampling doesn't work, and our main contribution was, and we're still going about it, so this is just one aspect, is design efficient sampling schemes to make the thing work well. That is small variance. So here's the notation. The notation is LK theta is the kth bit of the likelihood. L of theta is the likelihood. Little LK theta is the log of the kth bit, and L of theta is the total log likelihood. The method applies whenever the likelihood can be decomposed into independent piece of information, like panel data, maybe even time series data, and we construct an estimator such that the standard deviation is about 1. So it's important to be able to... so what I said was that simple random sampling just doesn't work, and I'll show you why. So here's if you look at the lower panel, I've got n equals 100,000 observations of people. So even when I sample 99% of the observations, my standard deviation is still 22. That's with simple random sampling. Of course, that's not the case with something more sophisticated. So that's simple independent random sampling. It just doesn't work. The thing just doesn't work. So what we do is, the reason it doesn't work is that you treat all pieces the same. Big chunks of log likelihood and small chunks you treat about the same. So we employ probability proportional to size, and we do simple random sampling with replacement. We do sampling with replacement because we don't lose much, but the variance of the log likelihood estimator is much easier to get. It's very hard to get sampling without replacement, so we use sampling with replacement. We can get very easily an unbiased estimator of it. And we try to get proxies so that the probability of selecting a chunk is proportional to the size of the chunk. And we don't lose very much by sampling with replacement instead of without replacement. We lose a little bit, but not much. That's a plot of that. Okay, so when you sample the likelihood unbiasedly, that doesn't mean you sample the likelihood unbiasedly. So what we want to do is do a bias correction so that our first estimate of the likelihood is L hat theta, which is x of little l theta. Z is normally distributed with a mean of 0 and a variance of sigma z squared, so that if in fact Z was normally distributed, we could, and we knew sigma z, we could have a perfect bias correction. But that's just not true. So the bias correction that we use is we estimate sigma z unbiasedly. We use an unbiased estimate of sigma z, so the question then is, are we doing something really approximate, or are we doing something okay? And basically, if we say that zk is LUK over P of UK, then and then form an estimate of the log likelihood, etc., then what we are doing is essentially, again, expanding the space. So now we've got an expanded space, and we've got a likelihood estimator PM hat depending on theta and u. That's the top line is x of LM hat minus that. PMY theta is our target. That's the likelihood, but it's not the true likelihood. We define the posterior density. That's the proxy posterior density, pi tilde m theta u, and then the marginal for that is pi tilde m theta. And that's, if we run an MCMC, that's our target. So how good are we? So basically, pi m theta is the joint density. MC produces iterates from pi m tilde theta on convergence. Now, we make some assumptions. I won't go through them, except that maybe they're reasonable. They are reasonable. I think we get the following results. First of all, I've skipped two. PMY theta, which is the pseudo likelihood that we're working with that depends on number of subsamples, is P of y theta, the percentage difference, is Cm theta over root of m, where Cm theta is bounded. So notice that the error depends on the subsample size. It does not depend on, and usually when we've got 1 million observations, the subsample size will be quite large, so the error will be very small. The posterior density is again of this form, so actually we can put bounds, and in the examples we've got, the posterior that we get, so now we're using non and unbiased estimate of the likelihood, but we're using the same theory. We get a pseudo likelihood and a pseudo target, but they're going to be very close because m is usually, when you've got big data, m is usually quite large. So we've got root of m to the minus a half here. We can show that these constants are pretty reasonable. And then we've got, again, that any moments are going to be close as well. And in practice, we find that, so basically in the assumptions, so this is the error. So in the bottom left corner is the difference between sigma z het theta minus sigma z squared. And you can't see the bottom, unfortunately, but neither can I, but that's very small. The histogram will show that that's very small. And we've checked out the assumptions. So at present, in the work that I'm going to present now, I'm looking at bankruptcy data. One, if a firm went bankrupt, 0 otherwise. We've got data set 2,000 firms, so that's not too big. And we've got the survival rate is given through this HT model with, and there's random effects here. And the way we treat the likelihood is that we integrate out the random effects through a trapezoidal rule. So the truth is stuff integrated out. And so when we use the trapezoidal rule, MCMC with h equals, so we can get an exact answer for this. For MCMC with h equals 0.01, we obtain an order of accuracy of 10 to the minus 9. And then we're using trapezoidal rule with h equals 0.5, 1.25, 1.50. And we are choosing the subsample size adaptively so that the standard deviation is 1 or about 1. And that's very important. That's why we need simple random sampling with, not simple random sampling with replacement, because we've got to work out that variance very quickly of the estimator. And we use random walk metropolis here. And so we're using the percentage of firms we use when h equals 1.5 is 1. H equals 1.25 in the trapezoidal rule is 1.2, and h equals 1.50 is percentage is 8. Now we're only getting, in this example, and we've nearly got another paper ready that we're doing much better, but in this example anyway, all I can say is we're getting between, say, 4 and 8 times the speed up for a given accuracy. But I believe we can do much, much better than this. And so that's the second part of the talk. The third part of the talk basically says, okay, we take the whole framework, but instead of doing MCMC, we try to deal with intractable likelihoods and using variational Bayes. And I'm going to talk about this. I've got about 7 minutes, right? Or if I go on past my time. So the proposed VB method, therefore, makes it possible to carry out Bayesian inference in some models where it was difficult to do before. And hopefully we have a generic method. We're still working on it in the sense that it can be applied to all statistical models. So introduction, Pn hat is again the unbiased estimator and is the parameter relating to how precisely we estimate the the likelihood. Z is the error in the log likelihood, so that's the error we talked about, and in the MCMC we wanted to make that the variance 1 down here. Now unbiasedness plays a role because the expected value of e to the z equals 1. This is so instead of working with u and theta, we can equivalently theoretically work with z and theta because z captures everything in the latent u's. So, so basically we propose to approximate pi of n theta z by variational Bayes. So instead of pi of theta, we've got q of lambda, and we have to estimate the parameters. So q of lambda theta is a variational distribution, often called the variational parameter. And the VB with intractable likelihood, what we're trying to do is estimate lambda in such a way that we minimize the Kullback-Leibler distance between q of lambda gn and pi n, which is the intractable likelihood that we'd really like to work with. And the gradient of KL is this, and we can unbiasedly estimate its expectation. And then we have an algorithm that iterates on lambda, just like many stochastic approximation algorithms do. I want to take an example, and then I want to wind up and just discuss things. So we take a state space model that's a very simple state space model. We can easily do it by MCMC. And, but again, it's a workhorse to demonstrate how these things work. The model parameters, there's 3 model parameters, and we compare the variational Bayes solution to the MCMC solution. And we find that the variational Bayes solution is not as good as the MC. It's not the same as the MCMC solution, which is the gold standard, but it comes close. And basically, it the CPU time to run variational Bayes was 9 and 233 minutes respectively. And so basically that's what I want to do is just summarize some of the stuff I've done and just talk about. I talked about MCMC with intractable likelihoods, and they can apply and discuss an application time series. I hope we can sort of and I know we can generalize things other people have to complex time series, spatial temporal models. Consider an approach to big data that could be combined with an approach to random effects models, etc. So the model can be more complicated. We looked at the big data problem where now we didn't look at an exact likelihood. We exact unbiased estimate. We used an approximation, but a very good approximation. One thing that I forgot to say, or didn't say, is that basically one of the assumptions in the theoretical analysis for optimality says that Z is independent of theta, but if we make the central limit theorem basically says that Z is going to be approximately normal, and by choosing the subsample M in such a way that the variance is constant, we make Z independent of theta. So we choose M, so it's variance, so the variance of Z, we choose M adaptively, so M depends on theta, so the variance of Z is constant, 1, irrespective of theta. That makes Z pretty much independent of theta in this particular case. And then I've also, and the strategy for the subsampling stuff is to use good ideas to obtain samples with small variances, and there's a lot of legs in that we're exploring, and this was early days for now in the stuff that I talked about. We're also sort of thinking hard about variational Bayes problems for intractable likelihoods and various other approaches like annealing and that for intractable likelihoods where we can modify or extend the theory we've got now for the MCMC stuff. So basically that's all I want to say for now. Thanks very much for listening.